Okay, this is Regents Chemistry Review, Session 4. In this session, we're going to focus on math and chemistry, all different kinds of math. Molarity, moles, percent composition. We're also going to talk about solutions and some math involved with Table G. So if you're having trouble with the math, this is probably a good session to review. So, 1 mole of something equals the gram formula mass. I've told you this before. We also know that 1 mole of something equals 22.4 liters if it's a gas, and that also equals 6.02 times 10 to the 23rd atoms. So you really should know those. They should be on a flashcard. 1 mole equals the GFM, which equals 22.4 liters if we're talking about a gas, which equals 6.02 times 10 to the 23rd, atoms, molecules, particles. There's different names that can have after it. This is not anywhere on the Regents reference table. That's something that's got to come from your noggin. Let's start off easy, calculating molecular mass. What is the molecular or formula mass of Na2CO3? When you see formula mass, they're really just asking for the GFM. So this becomes very simple because here you're just taking the element and you're timesing it by the number of atoms that you have for its mass. So here we've got Na, which is going to be 2 times 23, which is 46. You've got carbon, 1 times 12, which is 12, and you've got oxygen, 3 times 16, which is 48. And then I add all of that up, 14, 15, 16, 10, 106, 106 grams. Very simple. What is the formula mass of CuSO4? Same thing. Cu, 63.5. I only have one of them. S, 32. And oxygen, I've got 4 times 16, which is going to give me 64. I add this up. I'm going to get 7, 9, 12, 108. Let me just double it. 4, 5, 6, 7, 8, 9. And then 12, 15, 159.5, sorry, grams. There we go. What is the mass in grams of 3.5 moles of water? There's 2 ways that you can do this. First, you can simply plug and chug into the formula. Moles equals given mass over GFM. And you have 3.5 moles of water. You don't know the given mass, but you can find the GFM of water, H2O. So oxygen is 16 plus, you've got 2 times 1, 2 hydrogens times 1 for a total of 18. So water's always 18. So you can solve it this way. Put a 1 here and then cross multiply and divide. So you've got 3.5 times 18, which is going to give you 63 grams. Now when we get into some of these harder ones, it's so much easier to just use dimensional analysis as long as you know what your conversion factors are. So for example, I'm starting with 3.5 moles, and this is of course of water, and you know that 1 mole of anything is equal to the GFM, so 1 mole of water is equal to 18 grams. Well, I want to be left with grams, so I want moles to cancel, so I'm going to put 1 mole in the bottom, 18 grams in the top. Moles cancels, and this now becomes a multiplication problem. 3.5 times 18, which is 63, which is the same thing that I got over here. What is the mass of 1.2 times 10 to the 24 molecules of O2? So now they're having us go from molecules, which is using Avogadro's number, to mass, which is in grams. And unfortunately, you can't do this unless you use dimensional analysis. Now, do I think that they're going to ask you this one on the Regents? I don't think so, but I don't know 100% for sure, because the way that they're designing the questions to incorporate more reading and literacy, they could be changing what they're asking you to do. But if you know those three equivalents, 1 mole equals the GFM, 1 mole equals 22.4 liters, and 1 mole equals 6.02 times 10 to the 23rd molecules, then this is an easy problem because you've got 1.2 times 10 to the 24th molecules. And you're looking for grams. So basically, you want molecules to cancel. So you know 6.02 times 10 to the 23rd molecules needs to be in the bottom. Keep writing moles. And that equals 1 mole. So my molecules will cancel. But I am not to grams yet. Remember, I want grams. However, I do know another conversion factor. I know that 1 mole is equal to the GFM. And I am dealing with O2. So the mass of O2 is 2 times 16, which is 32 grams. So 1 mole is equal to 32 grams. So now my moles cancel. I'm left with grams, which makes me very happy. So this becomes a math problem. 1.2 times 10 to the 24th times 32 divided by 6.02, because this is in the denominator, times 10 to the 23rd. And when I do all that out, make sure you're using parentheses, you get 63.7 grams of O2, because you're going to do parentheses 1.2 times 10 to the 24th times 32 and a parentheses divided by 6.02 times 10 to the 23rd equals. What is the mass of 56 liters of CO2 at STP? Notice that this is a gas, and we know that 1 mole of anything equals 22.4 liters if it's a gas. So, what is the mass of 56 liters? Again, this is dimensional analysis. 56 liters. You know that 1 mole is equal to 22.4 liters. And this works out that you want liters on the bottom so that it cancels. I'm not to my answer yet because I'm not looking for moles. I'm looking for grams. I want mass. I know that 1 mole is equal to the GFM. What's my GFM of CO2? Well, you've got 12 for the carbon plus 2 times 16 on the oxygen, which is 32, which is going to give us a mass of 44 grams. So 1 mole equals 44 grams of CO2. Now my moles cancel. 56 times 44 divided by 22.4. And this is going to give me 67, wait, no, this is grams, I'm sorry. 56 times 44 divided by 22.4 is 110 grams of CO2. In this one, what is the volume occupied by 3 moles of nitrogen gas? Now they want us to find volume. So we're going to start with 3 moles of N2, and we know that 1 mole is equal to 22.4 liters. So now, because I'm asked for volume, I'm already done because moles cancel, and 3 times 22.4 is equal to 67.2 liters of N2. How many moles are present in 180 grams of NaOH? Well, again, I can do this one 2 ways. I can use my moles equals given mass over GFM, and I know I have 180 grams, and they don't give me the GFM of NaOH. Na is 1 times 23, O is 1 times 16, and H is simply 1 times 1. So 6, 7, 8, 9, 10, 2, 3, 4. So this comes out to be 40. So my GFM of NaOH is 40 grams. 180 divided by 40 is 4.5 moles. But again, you can do dimensional analysis, 180 grams, and you know that 1 mole equals 40 grams, which is the GFM. And this cancels. 180 divided by 40, 4.5. I get the same answer. What is the percent composition by mass of the elements in sodium sulfate? Remember that percent comp is equal to part over whole times 100. This is in reference table T. So in this case, they want us to find the percent of Na. They also want us to find the percent of S, and they want us to find the percent of O. So they want the N over the whole, the S over the whole, and the O over the whole. Well, let's find out what we're dealing with. We've got Na, which is 2 times 23, which gives me 46. We've got S, which is 1 times 32. And we've got O, which is 4 times 16, which is equal to 64. So this is going to give me 10, 12, 142. So my whole is 142 grams. And now we just have to do each one with the part. So N is going to be 46 over 142 times 100. S is going to be 32 times 142 times 100. And the last one is going to be 64 over 142 times 100. When I do these percentages out, you should get approximately 32.5% here, 22.5% here, and oxygen is 45%. And everything adds up to 100. The next one's a little tricky because they're asking you for the percentage of water by mass in sodium carbonate. The whole formula is sodium carbonate pentahydrate. That's the whole formula. Your part is the 5 waters. So you're going to have your part, which is the 5 waters, over the whole thing. So recall before that I told you water was 18. This is 16 plus 2 times 1 on the hydrogens. So that's a total of 18. And you've got 5 waters. So 5 times 18 for the water part is 90. That's your part. Now we've got to figure out what the whole is. So we've got Na, which is 2 times 23. You've got carbon, which is 1 times 12. And you've got oxygen, which is 3 times 16, which is 48. 8 and 2 is 10, and 6 is 16. 8, 9, and 10, 106 grams. So the whole is 90 plus 106, which is 196. That's the whole. So my part is my water over my whole times 100. And that's going to give me a percent of 45.9% water. Okay. A compound has an empirical formula of CH2 and a molecular mass of 42. Its molecular formula is. We haven't seen these in a very long time. First thing, find empirical mass. That's the first thing you're going to do. So if my empirical formula is CH2, carbon is 12, each hydrogen is 1, so that's 14. Second thing, you're going to take the molecular mass and divide it by the empirical mass. My molecular mass is 42. I'm going to divide that by my empirical mass, which is 14. It's always going to be the larger number divided by the smaller number because you need a whole number. So this is going to be 3. The 3 is my multiple, meaning that whatever my molecular formula is, it is 3 times that of my empirical. So I take my empirical formula, multiply it by my multiple, and I get C3H6. So find your empirical mass. That's whatever they gave you in here. Find the mass of that. Divide the larger number by the smaller number, so that's going to be molecular by empirical to get a whole number. And then multiply that back across the empirical formula to get the molecular. I don't think you're going to see a problem like number 2. They want to know a sample of a compound contains 24 grams of carbon and 64 grams of oxygen. What is the empirical? Well, first of all, you have to figure out what the molecular formula is. And the only way you can do that is to find moles. So for carbon, moles equals given mass, which is 24, divided by the gram formula mass, which is 12. It's the mass of carbon, and that gives you 2 moles. And then for oxygen, you have 64 grams divided by the GFM, which is 16. This gives you 4. So your formula is C2O4. They want the empirical. Remember, empirical means reduced. So 2 goes into 2 once, and 2 goes into 4 twice. So my empirical formula is CO2. Okay. How many moles of water will be produced from the complete combustion of 3 moles of ethane? One thing I want to say about moles. You're either going to be asked to find moles and you're going to use this formula, given mass over GFM, or dimensional analysis, or you're going to be given, so this is or, okay, or you're going to be given a balanced equation like you are in this problem right here. So then what you need to do is set up a proportion. So basically what I'm telling you is if you have a problem that asks for moles, if it's asking you to find moles and you don't have a balanced equation, you're going to use this right here, or dimensional analysis. If you're asking to find moles and you're given a balanced equation, then you're going to, like you are here, you're going to set up a proportion. How many moles of water? Put an X over the water, that's what you're trying to find, will be produced from the complete combustion of 3 moles of ethane. Put a 3 over your ethane. Now set up a proportion. You have 3 over what's in the balanced equation, 2, equals X over what you have in the balanced equation, 6. So you basically have 2x equals 18. Therefore, x equals 9 moles of H2O, because that's what you were finding. Now, you can also do this intuitively in some cases. You can see that the ratio between ethane and water is 2 to 6, which is the same as 1 to 3. So whatever I have here, it's going to be 3 times that. So if I have 3 moles here, 3 times 3 is 9. So 9 moles. But it's so much easier setting a portion because sometimes it doesn't always just work out evenly. You've got a fraction. Like here. How many moles of N2, I put an X here, are used to produce 5 moles of NH3, put a 5 here. My proportion is X over an unspoken 1 equals 5 over 2. So here I have 2x equals 5. So this isn't going to be even. These cancel, and therefore x is equal to 2.5 moles of N2. Let's talk about solutions. Solutions are homogeneous mixtures. All solutions are homogeneous. The solvent is the thing that's doing the dissolving, okay? The solute is the thing that's being dissolved. The solvent is the larger amount. The solute is the smaller amount. An aqueous solution, often denoted by AQ, means the solvent is water. It's been mixed with water. Concentration is the amount of solute per unit volume. We have three types of solutions. Saturated, that's when we're looking at table G, I sat on the line. When water will accept no more solute, it can hold all that it can possibly hold. Supersaturated means my data point is above the line, and that means that you have more solute than the solvent can actually hold, and eventually excess solute will precipitate out and be on the bottom of your flask or beaker. Unsaturated means that my data point is under the line and that the water can still hold more solute. There are a couple of terms that goes with these. If I have an unsaturated solution, meaning it can hold more solute, it's often referred to as dilute. If something is dilute, it can hold more solute. If something is supersaturated, it's often referred to as concentrated. It can't hold anymore. Solubility is the quantity of solute needed to saturate a given amount of water. For table G, this is measured in grams per 100 grams of water, grams of solute per 100 grams of water. This is important. The solubility of solids and liquids increase when temperature increases, but the solubility of gases decrease. Because remember, when gases increase in temperature, they spread out more, they collide, they're not going to want to go into solution. Okay, so let's try to solve some problems here. 70 grams of KNO3 and 50 grams at 50 Celsius and 100 grams of water. So they want to know what's happening. So what I would do is go to 50 degrees Celsius, 70 grams. Here's 50 degrees, 70 grams, and I'd put a dot. 50 degrees, 70 grams, 100 grams of water, so our water is good. And this is KNO3. So here's the KNO3 line right here, and this data point is below the line, so that makes it unsaturated. Which compounds are gases? Your gases are the ones with the negative slope. And that's because as temperature increases, the solubility of a gas decreases. And there are 3 of them. You've got SO2. Oops, I was trying to highlight it. That's not working. We'll circle them. SO2, NH3, and HCl. Those are the 3 with a negative slope. So let's write them in: HCl, NH3, SO2. 60 grams of HCl at 45 degrees Celsius. So let's go to 45 degrees Celsius. Let's go to 60 grams. And here's our data point. So our data point is right on the HCl line, so that means it is saturated. 20 grams of SO2 in at 20 degrees Celsius. So here's 20 degrees Celsius, 20 grams. And we're talking about SO2. Here's SO2. It's above the line, so this is going to be supersaturated. Even though it says no precipitate on the bottom of the container, it eventually will fall out and it'll precipitate. Okay, now they're getting tricky on us. On the next one, they've changed the grams of water. You have to be careful when they change the grams of water. In these last two, they've changed the water. It's no longer 100 grams. So you need to set up a proportion to determine what it would be in 100 grams. So we've got 20 grams in 50 grams. So I'm going to write that down over here. I've got 20 grams of solute, so NaCl, in 50 grams of H2O. Well, how much would it hold in 100 grams of water? Because then I can see what happens on the chart. So we can cross multiply and divide here. I've got 20 grams times 100 grams divided by 50 grams, and that's going to give me 40 grams of NaCl. So I'm going to go back to 90 degrees, and I'm going to go 40 grams. So it's right on the line, so that means that I'm really dealing with a saturated solution here. I couldn't directly just plot this information on the graph because it was for 50 grams of water. Now, it should make sense intuitively that if I have 20 grams in 50 grams of water, that it would be 40 grams in 100 grams, because this is half of what the amount of water that I have. But it's easier to set it up as a proportion and solve because it may not always be an even number. In the next one, it says I've got 20 grams in 200 grams of water. Well, if I have 20 grams in 200 grams of water, then what would I have in 100 grams of water? Well, 200 is double 100. So if I have 20 in 200, then when you solve for this, you'll see that x is 10. So that means that I've got 10 grams in 100 grams of water. So I go to 90 degrees, 10 grams. Now where is my data point in relation to NaCl? It's below the line, so this would be unsaturated. So please watch the water on this. You may have to multiply or divide to get the number you're looking for before you can actually plot it on the chart. All right, let's talk about Table F, solubility guidelines. Remember, anything on the left is soluble unless you meet the exception. Everything on the right is insoluble unless you meet the exception. So, for example, if I had PbCl2 and I wanted to know whether it was soluble or not, I would go to the negative ion. These are the negative ions. You're going to look up chlorine. Chlorine's over here. It's soluble unless combined with silver, lead, or mercury. There's my exception. So this is insoluble. If I were to look up Na2CO3, I'm looking up the CO3, the carbonate. Carbonates are insoluble unless combined with group 1 or ammonium. Well, Na is a group 1 element, so this is going to be soluble. Because I've met the exception, the opposite happens. Let's look at a couple of these. Remember that an electrolyte is something that conducts electricity or has the potential to conduct an electric current. Electrolytes are acids, bases, or salts. So if I have an acid, base, or salt, it has the potential to conduct an electric current. So what we're going to do is we're going to determine whether something's soluble or insoluble. If it's soluble, then we're going to talk about how many moles of ions does it produce when it dissociates in water, and then whether it's an electrolyte or not, and if the freezing point increases or decreases. So let's look at Ag2SO4. We're going to find the SO4 first. The SO4 is soluble unless combined with, oh, there it is, Ag. So this is going to be insoluble. So since it's insoluble, we're not even going to answer the rest of this because that means it forms a precipitate. NH4NO3. Here's NH4. Oh, we're not interested in that. NO3. We're interested in the second part, remember. NO3 is soluble, no exceptions. So this is soluble. If this dissociates in water, it's going to dissociate into two ions, NH4 plus and NO3 minus. So that's 2 moles of ions. This dissociates into, what I mean by dissociate, NH4, NO3, dissociates into NH4 plus and NO3 minus. 1, 2, 2 ions. It is an electrolyte. So if it's an electrolyte, remember, hot gets hotter and cold gets colder. So the freezing point is going to decrease and the boiling point is going to increase because cold gets colder, hot gets hotter. CaCrO4. CrO4 is here. It's insoluble unless combined with group 1 calcium. There's the exception. So we looked up chromium. It met the exception, so it's soluble. So this is going to dissociate into CaCrO4 dissociates into Ca2 plus CrO4 2 minus. 1, 2, 2 ions. Electrolyte, yes. Cold gets colder, hot gets hotter. ClO4. ClO4 is here on the left, the soluble side. No exceptions, so this is soluble. This would dissociate into Fr plus 1 and ClO4 minus. So 2 ions, yes, decreases, increases. BaOH2, let's look up our hydroxides. Our hydroxides are insoluble unless combined with group 1 calcium, barium, strontium. So there's our exception. So this is going to be soluble. This dissociates into, this one's slightly different. We've got Ba2 plus, we have 2 OH minus. So I've got 2 plus 1 is 3. 3. So when we look at this, remember the more ions that you have, or the more pieces, the greater the effect on the freezing and boiling point. So this, the barium hydroxide in this case, would have the greatest effect on the freezing and boiling point. It would lower it more. It would lower the freezing point and raise the boiling point more than these guys, because these guys all have 2. Remember anything that is covalent. Covalent. So C6H12O6. This is all covalent. This does not dissociate in water. All covalent compounds are always assigned a 1. So if I gave you 4 things, NaCl, MgCl2, and C6H12O6, and I asked you which one had the greatest effect on boiling and freezing point. NaCl is 2 pieces, or 2 ions, Na plus Cl minus. MgCl2 is going to be 3. 1 Mg, 2 Cls. This is covalent, it's 1. So this one has the greatest effect. Okay, almost done. Let's talk about molarity. Molarity is a concentration term, and it refers to the number of moles of solute per 1 liter of solution. In other words, if I have a 3 molar solution, that's 3 moles of solute per 1 liter of solution. A 0.5 molar solution is 0.5 moles of solute per liter of solution. So they're asking you to find molarity here. Molarity equals moles over liters of a solution that contains 4 grams of sodium hydroxide and 500 mils of solution. First of all, you need to know how to convert milliliters to liters. And you know that 1,000 milliliters is equal to 1 liter. So if I have 500 milliliters, dimensional analysis, 1,000 milliliters equals 1 liter. Milliliters cancel. So 500 divided by 1,000 is 0.5 liters. So I know that this is going to be 0.5 liters in the denominator. I don't know my moles, but I can get my moles because moles equals given mass divided by GFM. And I'm told I have 4 grams, and I'm told the GFM is 40. So 4 divided by 40 is 0.1 moles. I can then take this answer and put it over here, 0.1 moles. So 0.1 divided by 0.5 is equal to 0.2 molar NaOH, and that's my answer. So a lot of these molarity problems are 2 steps, okay? Sometimes you can do the straight molarity if you have the moles and the liters. Sometimes you have to use your mole formula first to find the moles. So what is the molarity of a solution that contains 28 grams of KOH in 2 liters of solution? So I have my 2 liters. I don't have to change between milliliters and liters. I don't have my moles, but I know moles is equal to given mass, which is 28, divided by GFM, which they gave me is 56. So this is going to be 0.5 moles. It's 1/2. So I can take my answer, 0.5 moles divided by 2 is going to give me 0.25 molar KOH, and that's my answer. Let's briefly talk about density. We don't really talk about density in chemistry, but you have density values in table S, and they sometimes will ask you to find density or mass or volume. The density formula is found in table T. So here you're given the density and they want to know the mass. Well, you know that 1 mole of anything is equal to 22.4 liters, and this is a gas. So density is equal to mass divided by volume. They gave you the density 1.96 grams per liter. And why am I setting up dimensional analysis? So you've got 1.96 grams per liter equals, we don't know the mass, but we know the volume is 22.4 liters. So you can just simply put a 1 here, cross multiply, x equals 22.4 times 1.96, and that's going to equal 43.9 grams. And in this last problem it says what is the density? So now you're finding density of carbon dioxide, STP. So that's kind of leaves you wondering what to do, because density equals mass divided by volume. Well, we know the mass of CO2 is 44 grams, 12 for carbon plus 2 times 16 for the oxygen is equal to 44. So 44 grams. And the volume of CO2, well, we know 1 mole is equal to 22.4 liters. So 44 divided by 22.4 is 1.96 grams per liter. Another way that they could say this, and this is our last problem here, is they could say, what is the volume of 1 mole of neon? So you know density equals mass divided by volume. So if you look up density, go to table S, and the density of neon in table S is 0.000825 grams per cm cube, equal to mass. Okay, what's the mass of neon? The mass of neon is 20 grams over the volume. You don't know that. So you can put a 1 here, and so you've got 0.000825x equal to 20, and then divide both sides by that. You're going to get a very large number here. 825. These cancel. And in this case, x equals 24,242, and grams cancel, so cm cube. Okay, that's a lot of math in a short amount of time. Have a great afternoon.